Before a virtual world can exist, there is only a mathematical void. To build reality, a computer must define a single point of origin. From that origin, three lines extend, x, y, and z, forming the world coordinate system. This grid is the absolute anchor. But physical devices bring localized coordinate systems. Every object operates relative to its own local zero. This spatial calibration framework connects three distinct coordinate systems. The AR headset maintains a local frame tracking head orientation. Simultaneously, the robotic arm relies on a stationary base frame to compute dynamic reach. The global world system acts as the translation bridge. To pick up a virtual object with a physical machine, the software maps the headset's local movements to the global world space, and then translates those coordinates into the robot's local base frame. Without continuous matrix synchronization, sub-millimeter interaction is impossible. Once the coordinate grid is established, the software needs a method to sculpt physical forms. Objects are constructed using boundary representations, which define solid shapes by mapping their exact outer surfaces and edges in 3D space. This comparison illustrates two ways to define surfaces. On the left, exact mathematical models using continuous curves. On the right, faceted models built from flat polygonal planes. Calculating true curves demands intense processing. To maintain speed, the industry standard relies on faceted representations. These boundaries are often generated algorithmically. A system can extract geometric data from a flat two-dimensional sketch and extrapolate it into a complete three-dimensional volume. Real-time rendering requires aggressive efficiency. Approximating complex curves with flat polygonal geometry allows systems to maintain the high frame rates required to prevent motion sickness. Software updates objects using matrix mathematics called geometrical transformations. Translation slides the geometry along the axes. Rotation spins the coordinates around a central axis. Scaling forces the object to expand or contract, and shearing slants the geometry out of perfect alignment. When you reach out to grab a virtual item, you are seeing these equations execute up to 90 times a second. Matrix operations power the illusion of physical collision, weight, and movement. Constructing the environment is half the pipeline. To present this 3D data to a human eye, the system introduces a virtual observer, a software camera designed to mimic optical reception. Every render begins at the center of projection. This is the exact spatial origin of the viewer's gaze, anchored at specific x, y, and z coordinates within the world system. From here, direction angles determine the precise line of sight. Directly in front of the camera sits the projection plane, or viewport. Because headset lenses are flat, the 3D scene must be drawn onto a two-dimensional surface. To execute this conversion, the system traces an imaginary straight line from the center of projection to every visible vertex on the 3D models in the distance. Where these lines intersect the projection plane, the software draws a pixel. This technique compresses the geometry based on distance. Because the projection lines narrow as they approach the camera lens, an object placed further away intersects a smaller area on the viewport, mimicking how human vision perceives scale. This schematic shows a three-point perspective projection. When the projection plane intersects all three spatial axes, the lines converge toward three distinct vanishing points, establishing steep, aggressive depth. Virtual reality does not project actual depth. It forces a two-dimensional optical illusion onto a flat display, using the strict geometry of linear intersection. To optimize rendering, the camera is constrained by a viewing frustum. This diagram outlines the geometric bounding volume. The expanding walls of this truncated pyramid are mapped by field of view angles. The volume is capped on either end by the near and far clip planes. They set strict mathematical limits on the minimum and maximum depths the camera can perceive. This illustration details how the system handles the surrounding environment. Objects residing inside the frustum are rendered. The engine completely discards any model located entirely behind the camera, outside the field of view, or beyond the far clip plane. Second, if an object intersects any of the clipping boundaries, the software mathematically secars the geometry at the plane. Only the internal vertices are processed for the final image. A virtual world often contains massive, sprawling cities. 3D clipping is a computational survival mechanism, ensuring the hardware only calculates the exact polygons visible to the user at any given millisecond. With the visible geometry isolated inside the frustum, the engine must assign material properties to the surviving polygons before it can calculate light. This standard color wheel establishes chromatic relationships. In a graphics engine, color is assigned as a numerical base value that dictates exactly which wavelengths of simulated light a material will absorb or reflect. Selecting colors from opposite sides of the wheel yields a complementary scheme. The resulting high contrast forces a stark visual hierarchy, directing the user's attention directly to critical interfaces or target objects. Conversely, this chart details analogous color groupings. Placing neighboring colors together or using monochromatic variations of a single hue generates visual harmony and establishes a readable depth of field without clashing. Color is a mathematical base value. It provides the core data determining how the surface will react once simulated photons strike it. Real-time graphics systems simply cannot afford the massive processing time required to trace millions of actual bouncing photons. Instead, they rely on empirical illumination models to calculate quick mathematical approximations of light physics. This diagram maps the 4 vectors required to execute that calculation: light source, surface normal, reflection direction, and viewer position. The light source vector, intersecting the perpendicular surface normal, establishes the exact angle of incidence. The reflection vector dictates the outgoing bounce. By pairing this trajectory against the viewer position, the software determines precisely how much light energy aligns with the camera lens. Different shading algorithms interpret these vectors to simulate distinct materials. Lambertian shading calculates matte surfaces, scattering the diffuse reflection evenly across the polygon regardless of where the viewer is standing. Phong illumination calculates glossy surfaces. It tracks the intense specular highlights created by direct light, producing sharp reflections that change rapidly depending entirely on the angle of the viewer vector. The Blin-Phong model optimizes these calculations. By modifying the angle math, it generates smoother specular highlights with significantly less friction on the processor. This is the reality pipeline. Local boundaries multiply by matrices, culled by the viewing frustum, projected through an imaginary plane, and shaded by vector light. An immersive virtual environment is built entirely on mathematical efficiency. It is a continuous, hyper-fast sequence of geometric pruning and optical simulation, calculated exclusively to intercept and convince the human eye.